I'll get started. So, welcome to the afternoon. And what I'm going to do in this lecture is I'm going to still focus on producing more examples of left orderable and bi-orderable groups. But there's a huge group of people coming, so no, just a few. It's okay. Come on in. I just started. I'll just pause.
Too many dumplings, sorry.
Okay, so I'm going to focus on making new groups from old. And the way I'm going to do it is by investigating how left orderability and bi-orderability behave with respect to standard group theoretical experiments, like taking quotients, taking few products, direct products, amalgams, that sort of thing. So let's start with the easiest thing first, which is direct products. And you'll probably notice there's not really anything that's very easy. So the proposition is that the direct product two groups is LO, or of course PO, if and only if factors are. And the whole point is that you just use the lexicographic construction that I used in the short exact sequence argument in the last lecture. So use lex ordering. But of course, this is a special case. You might want to take an arbitrary product. So I'll say, what about something like this? Where these are all notable. So same thing. You can either make some appeal to finitely generated subgroups, or you can construct the ordering directly by making a lexicographic ordering of this product, where you have to choose a well ordering of the index set in order to make it make sense. You have to be able to look at which index is the first thing where two elements of this differ, and then say one is bigger than the other. And to make that make sense, you have to do a well ordering of the index set and use that to construct the lex. But this is the easy case. There's really not much to say about direct products. They work. So then next, let me say, what about quotients? So quotients. This is only slightly more difficult, and even then, not that much. So we already saw the notion of convex. So I'm going to write down the definition because it's easy to do in a left orderable setting. So what we need here is we need the idea of convex subgroups. So subgroup H and D is convex with respect to the left order less than of G if for all G and H in H and F in G, this implication, so G less than F less than H, implies F in H holds. And again, like Kai's picture was completely right. If you're thinking of these groups as being on a line and the identity is here, convex subgroups are some sort of interval around the identity. And you may want to specify what it means for a subgroup to be convex with respect to some order, even if you don't have an order of the big group in your hands. And that is called relatively convex. So a subgroup H of G is relatively convex if there exists an order of G relative to which it's convex. Okay, and now how can you left order quotients? Well, it'd be exactly quotient by these things. That's when the quotient is left orderable. So this is a proposition. So suppose P is LO, and you've got a normal subgroup N. Then the quotient is LO if and only if n is relatively convex. So I'll do a little bit of a proof, but not much. So what I want to say is, if this quotient is left orderable, then you have to produce an ordering of G relative to which this is a convex subgroup. And that's exactly the lexicographic ordering. So you do the only construction that makes sense in order to build an ordering on G from an ordering on here. And you can put one on here because we're assuming G is left orderable. So then you build something in the middle of your short exact sequence. The other way is, you want to just say that you can order the quotient by using coset representatives in order to say which is bigger than the other. And that works exactly because n is convex. So let me just say this direction. So suppose n is, well, I don't know how to say this in words, but convex with respect to this order. Then the way we want to define the ordering on the cosets is just look at coset representatives. So then define, I'll use curly less than on the quotient by the only way you can. So just talk about positive cones. So I'll say this element is positive, bigger than the identity, if and only if H is bigger than identity in this order. And then if you want to check that this is well defined, I'll just say exercise, it's well defined, and it's exactly this convexity. So it's well defined exactly because of convexity. And there is something to prove there, but it's like one line. And then once you know that this is well defined, well, it's definitely going to be left invariant, and it's definitely going to be total. So it ends up, this is what you need. So that means that direct products, quotients, basically not mysterious at all. Direct products are always left orderable or bi-orderable, depending on the factors. Quotients, of course, it's not always going to be left orderable or bi-orderable in any quotient, because you could even introduce torsion. But the thing that you're looking for is exactly that the thing you're quotienting by is relatively convex. Okay. So now the first thing of interest, where we have to actually do something, is free products. So free products, yeah.
Is every left orderable group a non-trivial quotient, so a left orderable group by a convex subgroup?
Yeah, because you can just take, well, take a free group. And that's
the subgroup that you're quotienting by necessarily convex when you do that.
Yeah, because you can always build it by doing the short exact sequence argument to make a lexicographic order on the thing that you're quotienting from. Yeah, exactly. So it's just, yeah, because every group is going to be a quotient of some free group, it's exactly that everyone arises as a quotient like this too. Yeah.
It might be illuminating to mention that being convex is an extremely rare property.
Oh yeah, yeah, quite special. Like it's very, very easy to break left orderability and end up with something that's not left orderable at all. In fact, yeah, hard to find convex subgroups if you're challenged to find one. Yeah, I guess that's a good point, because I said this sort of like, oh, it's obvious. You just look for these groups and then you take their quotients, but it's not that easy. Yeah. Okay, so then free products. Free products work out the same way as direct products, where they're also going to be left orderable or bi-orderable, depending exactly on the factors, but it's a little harder to say why. So let's write it down. The group free product of G and H is left orderable if and only if G and H left orderable. And I'm just going to do left orderable, and then I'll do bi-orderable in a separate case, because I want to sort of emphasize that there's a lot more work that goes into the different approaches. So, okay, how would I show that this is left orderable? I'm going to show two proofs. One, which is sort of like a slick existence theorem that shows, yeah, it's left orderable, but if you were challenged to actually work with it, it might be a bit messy. And then a second approach that answers a question from the first lecture, which was, isn't there an order on the free group where I can actually say what the signs of elements are quite easily, some sort of formulaic thing. And then I'll say, yes, there is. And it comes from a general construction that works in this setting. So the first proof is you sort of cheat a bit. This is going to be pretty unsatisfying, but it gets the answer. So look, you got, so there's two maps. So there are maps. You know, G maps to the identity, H maps to identity H. They go from G to the direct product of G and H, H to the direct product of the G and H. So these induce a map like this. So you go from the free product of G and H to the direct product of G and H, right? That's what these do.
And the kernel's free.
Yeah, and the kernel's free. So you just do this. And if you're wondering what this is, you know, elements appear, you can write them out as a word, right? A1, A2, AN, where these are alternating from G and H. And then what this map is just let everything commute, right? Like the things from H can pass by the things of G, the things from G can pass by the things of H. And whatever you've got left in the H, in the G component, you put it there. Whatever you have left of the H component, you put it there. So there you go. There is a map like this. So yeah, now we write down the kernel of that happens to be free. I'll actually write down what a free generating set is. And if you sort of opt to not look at the notes that I have and instead do it yourself, you can just use normal forms of words to show that the generating set I write is going to be the free generating set. So, so this gives an exact sequence. Of this K. And it happens that K is free. K is free. And the generating set is exactly all the commutators. So it's these guys, G, H. You know, this should be explicit. Where G is a non-identity element of G. And H is a non-identity element of H. Yeah, so there you go. And then an arbitrary free group is going to be left orderable of any cardinality because of the finitely generated subgroups all being free. And so this is definitely a left orderable group. This is left orderable by a lexicographic construction, and we left over the middle. There you go. But you see, it's a little bit unsatisfying, although it does have one property that is kind of desirable, is that note, we can left order the free product in a way that extends a given left ordering of G and H by using this construction, which is how you would hope that it would work. And it does work that way, even if you do this sort of cheap trick. So this allows for left order of G free product H, extending a given left order of G and of H, which is sort of what you would want to happen. But I will say pretty unsatisfying in the sense that anything which is in here is just a total mystery. Like, how would you order those? Well, it's some sort of existence thing about there's left orders on arbitrary free products. And yeah. So let's see if we can have a formula that will actually tell us how to order things. And that's what the next technique of proof is. So
Are there any cardinality assumptions on the G and H? Are they like finally generated or something? Or?
no, you don't need anything. Yeah, but I mean, you do end up with a big, pretty awful sized free group if there's no cardinality assumptions, but it's still left orderable just by looking at finally generated subgroups, and they're all free.
Okay.
So yeah. Yeah, so then that's proof one. Proof two. This is definitely not by me. This is Sunic and Dix and their method, which works in much more generality than what I'm going to say. This is just for free products. So what I want to do is I want to tell you a function now, which goes from here to the integers. And what you do is you compute the value of tau from, well, I said every word has a normal form, right? So what we're going to do is we're going to say how to compute tau from the normal form of a word. And then what we'll do is we'll just say, if elements go to a positive number, they're positive. And that'll work. So It's a little bit messy, so let's just walk through what the definition of this is, and then I'll say it's a little case argument to check it works. So start with positive cones. Positive cone PG and G, PH and H. Now, given a non-identity element W in the free product, write it as this normal form, A1, A2, A3, up to AN, right? Now, where these come from, so the AIs are all from G without the identity and H without the identity. Now, there are three sort of cases I want to consider. This could start with something in G and end with something in H, or it could start with something in H and end with something in G, or it could start and end in the same group, right? This could be in G, this could be in G, this could be in H, this could be in H. I want to sort of say what to do in each of those cases in order to build this tau. So we first define some quantity eta of W, which exactly is going to keep track of which case we're in. So we want it to be 0, first of all, if the length of W is 1. So there's no starting and ending in different groups to worry about if it's just a single group element, right? And so in that case, I just want to say this quantity I'm defining eta is 0. Now, if this is like an actual word in alternating group elements, I want eta to keep track of if it's starting at G, ending in H, or whatever. And so I'm going to say this is equal to 0 if A1 and AN are both in the same group, so both in G or both in H. And then I want it to be 1 if it starts in G and ends in H, and -1 if it's the other way, starts in H and ends in G. Okay, now I'm going to tell you how to define tau. Now set tau of W. Remember, W is this alternating A's, right? So tau of W is equal to, I'll write it and then I'll. So this is the count of A's that are positive in one of the fixed orderings. And then we want to go minus the count of A's that are negative in one of the fixed orderings. And then we say plus eta. Okay. So, right, so this is what we're doing. We're going through and counting up how many of the things that appear here are positive in one of the factors, G or H, and how many are negative. And then we're taking the difference and we're adding this fudge factor of eta to take into account which factor we started in and which one we ended in. And miraculously, this works. So then set P be equal to all the W's. Well, I'll be careful here. W in this, but not the identity. Such that tau of W is bigger than 0. It works. That is the positive cone of an ordering. So how would you check this? Well, first you got to be sure that nothing's mapping to 0 so that everything gets assigned a sign. And the way that you do that is you can check case by case that this is always odd. So I'll just say this works. To check, first find it's always odd, right? And that's going to take care of the problem that, you know, maybe there would be some group elements that weren't assigned a sign, you know, positive or negative by this prescription. But no, they're all assigned a sign because the things that go to 0 are well, nothing goes to 0. Yeah, the identity, yeah. And And then the other thing is you need to check that this is a semi-group as well, right? And to do that, this is just a case-by-case argument where you take normal forms of words and you concatenate them and you see what happens. So, and I'll just say check cases. Right, and of course, the reason you have to do cases is because the different possibilities for eta depending on where a word starts and finishes. Show P dot P is P didn't P. Yeah, and it works.
Is this where, sorry, is this like why you introduced this eta to somehow like?
Yeah, just to track the, because I could either say the cases here or say the cases here. And then so yeah. You just introduce eta to track the beginning and the end. Or there's another way of writing this down, which is allows you to generalize this to sort of more general products than just two elements, which is you write this as number of positive elements minus number of negative elements, and then this quantity, you deal with it by, so you sort of order the index set of your free product, and then you count the number of times that you go up when you pass from one element to the next, like up in index, and the number of times you go down as you go in. And then that generalizes this quantity eta so that you can use this formula for general free products. Yeah, but doing two, I figured this is the best way to say it. Yeah, and basically, you know, presented like this, I'm well aware of the fact that it just looks like magic, but there's a very good reason for this to happen. And so I encourage you to go and read their paper if you're curious how this ever happened. But it's great because this answers the question from the first lecture of, you know, isn't there an order? I can just look at the element and say what its sign is. And yeah, for free groups now you can just do it. You can actually just use this to tell yourself the sign of a given element.
Sorry, can I ask another question?
Yeah.
You get a different order than if you were to just do like the.
Is it different than this? Yeah. Yeah, it's different for sure. Okay. So orders of free products is the next thing I want to do. And the first thing I want to do is point out that neither of the things we just did is going to help you buy order a free product, right? And so let me just say why. So remark, these don't buy order free products. In the first case, A is free, so we can left order it, you know, in the first argument we did. But we would need to find an order on it that's invariant under conjugation. And I don't know how to do that. Maybe somebody else is going to tell me that it's possible, but to my knowledge, it can't be done. So A is free. We need BO on K invariant under conjugation to use a short exact sequence. And I don't know how to do that. Two, this tau function, it's just, it doesn't give by ordering, so you can just check. So for instance, let's pick G and G without the identity, H and H without the identity. Then if you just look at this, tau GH, that's 1, so it's positive. Or maybe that's not 1. I think it's 1. In any event, it's positive. I'll say that just so I know I'm not saying something wrong. Sorry. I want to choose this in here, in here. Oh, then yeah. And that's right. H less than identity. The point is I have to choose them in the factors with prescribed signs in order to be able to keep this. All right, so I'm choosing G from here that's positive in the given ordering of G, H from here that's negative in the given ordering of H, then that works out. Okay, so GH, identity. And then, but if you compute, you know, tau of the conjugate of this, then that's going to end up being tau of HG, which is -1. So I changed sign when I conjugated, and that's bad. So it's not a by order. This is all meant to justify the fact that I'm about to sort of put you through something pretty difficult. So let's see how we by order a free product of two bi-orderable groups. And I will say, you know, there is a way of wrapping your head around it a little bit. If you think of it as, remember the strategy for by-ordering a free group where I didn't do the details, but I said, here's how you do it, is you build an embedding of the free group into some, in the case of the first lecture that I gave, you build the embedding of the free group into, this ring of formal power series and non-commuting variables, and then you have a bi-order on a specific subgroup of that, which restricts to the image of the embedding you built. We're going to do the same thing, but we have to do it a little bit more sophisticatedly in order to embed an arbitrary free product of bi-orderable groups into something. So here's the theorem. It's due to Vinogradov, but I believe the proof that I'm about to follow is due to Bergman. So here we go. The free product is G and H is bi-orderable if and only if G and H are bi-orderable. So we're just going to do a sketch of this. So what I'm going to do is I'm going to sort of build all of the pieces and then say it works, and you can check it if you are so inclined. So I'll just say this is sketch. I guess a lot of what I'm doing is sketching, but here we go. First, I want you to Lex order the direct product using a bi-order on each factor to create an ordering on this direct product. Now, I want you to extend this order to an order of this guy. So I'll call it capital gamma. It's the integer group ring of direct product. So things in here are finite formal sums with integer coefficients of things from here, right? So basically polynomials, you can think of them. And I want to tell you how to extend this to an order of this. The way to do it is, or a way to easily think about it is, think about the underlying abelian group of this, right? So the underlying abelian group of gamma is, this great big sum of copies of the integer. The integer is indexed by, elements in the direct product. And basically, I want you to bi-order this lexicographically or reverse lexicographically. So order this sum using the given bi-order of the index set. We think this, order the index set. So I hope that makes sense. What I mean is, given two elements in here, I'll say it in the language of this, but this is sort of the slickest way to say it. In the language of this, think about two finite formal sums in here. Coefficients in Z, terms from here. What you do is you compare them on the smallest term relative to this ordering of these terms. And then you look at the Z coefficients and you say which one is bigger based upon the Z coefficients that you see there. So now I want to say we've successfully ordered this, and I just want to use the same symbol for that order. So now we have this ordering on gamma. Okay, we have to go one step further. Now I want to do the following. I want to take this order of gamma and I want to extend it to an order of something even bigger. So I want to extend this to an order of, well, I'll just write it. So 2 by 2 matrices with entries being polynomials in variable t and coefficients coming from this gamma. And now I just want to say, how do we order this? So here's how to extend this ordering to that. So everything in here, these are 2 by 2 matrices. So what I want to do is I want to look at a 2 by 2 matrix and choose an arbitrary ordering of the entries. We have to decide which one is going to be called first, second, third, and fourth, right? And so I'll just say, this is the first entry, this is the second entry, this is the third, this is the fourth, right? So our order, the entries, say, you know, in the obvious way, it's like A11 is the first, A12, A21, A22. And it doesn't matter which way you order them. You just have to pick one and stick with it. Now, consider an element. So that's going to be something that you can write like this. So I equals 0 to n, m, I, d, I. Right. Well, I mean, it's a matrix of polynomial entries, but you can pull the matrix out fine and keep the coefficients next to the matrix like that. Now I want to tell you, when is this bigger than the identity 0? And so here's what I want you to do. For a given element, let's say that MK is going to be the first non-zero matrix in the expression for this written this way. Let MK be the first non-zero matrix in this expression. Now, what I want to do is I want to declare this thing to be bigger than 0 if, when you look at the first non-zero matrix in that expression, the first non-zero entry in that non-zero matrix is positive. And so you see, when I say first entry, I mean relative to our fixed ordering of the entries. So then declare this sum bigger than 0 if first non-zero entry in MK, which is the first non-zero matrix in that expression, is positive with respect to this, or the ordering that we already defined on this. And then, you know, in general, the way that you would compare two elements then is, you know, you look at the first, if you take two expressions of this form, you look at the first matrix in the sums where they differ, and you look at the first entry in the first matrix where they're different, and then you compare the two entries using the ordering of gamma. Okay, so we're like, you know, 3 or 4 levels deep at this point. I hope it's okay. Now's the end of it. Okay, so we're there. So now what I want to do is I want to say, this matrix ring that I've just defined, that's the thing that we're going to use in place of, you know, the ring of formal power series and non-commuting variables. We're going to take our free product and embed it in there. And then I'm going to say, and the order that I've defined happens to be a bi-ordering on the image of our embedding. So let me tell you what the embedding is. We'll define a homomorphism. So from the free product here follows. So, I mean, I'm defining a homomorphism from the free product, so I just have to tell you what to do to an element of G or an element of H, right? So I'll say that I want you to take G and map it to this matrix. So I'll write it out in all of its detail. And so remember, entries should be from here. So this is a constant polynomial entry. And then 0 down here. And then you see, I want to send the H's to lower triangular matrices that, you know, look similar. And we send H to this. Now, together, these give us a homomorphism like this, and it happens that it's an embedding. So this induces an embedding the free product into the matrix ring that we built. So perhaps you've seen this sort of famous argument before, where you embed the free group into a group of matrices by sending one generator to an upper triangular matrix, the other generator to a lower triangular matrix, and you do this kind of ping pong argument to say, and it's an embedding. This is exactly a generalization of this, where to show this as an embedding, there's some sort of ping pong argument that you do based upon looking at the powers of t that appear in the different entries of the matrices. And you can show that, well, you can show that there's a partition of these matrices into 3 sets, and that the first set always ends up being tossed into the second, and the first set always ends up being tossed into the third. So it never comes back to itself, depending on whether or not you're sort of taking a word here that starts or ends in G or H. So I'll say from here, use a ping pong argument, so it's an embedding. Of course, that's not actually the bad part. The bad part is checking that the order I've defined is a bi-order when restricted to the embedding. It is. So the order we defined on M2 gamma T, bi-order is the image. And I mean, you can well imagine that that's going to be a little bit hairy to walk through, but you can do it. It's all there and you just need to pick it apart.
So the order on M2 gamma T is order with respect to the ring structure.
I don't think it becomes an ordered ring with this order.
So it's only about the addition.
Well, what I mean is, I think that everything behaves nicely if you restrict to the image of this map. But I think that in general, if you think about the order on the whole group, it's not behaved so nicely that it's an ordered ring.
For all the steps up to this point, when you were saying it, that it's ordered, you just meant as a set. Like it's not.
Yeah. I don't want to claim any invariance properties about the order until I restrict my attention to the image of this map. And then it's okay.
Because you only declare it's greater than 0. You didn't say it's like in order there.
Yeah, but you're right. I only wrote what it means to be greater than 0, but then I said in words, I said, and if you have 2 that are different, you compare them by, yeah, but you're right. I would have to say more than just comparing it to 0 if I wanted to be very careful. Yeah. Okay, so there you go. 3 products of bi-order groups are bi-orderable. Now, believe it or not, now comes the hard part, as if this wasn't bad enough. So what if you want to left order or bi-order amalgams? That's what our next thing is going to be. So I'll say, what about amalgams? And we'll just stick to a very simple case of 2 factors. So let me write down exactly what I mean so that we have some notation and so that you know what I'm saying if you haven't heard people talk about amalgams before. So we'll just say, suppose A, G, H are groups. A has injective homomorphisms in 1 from A to G, 2 from A to H, and then set S to be equal to all the things of this form. P1 of A, P2 of A, inverse A ranges over all the elements of A. Right, and then I want to take the free product and quotient by the normal closure of S. And that's my amalgam. And all I want to know is when is that left orderable? Quotient by normal closure of S. When is this? Oh, turns out that's really bad. So this was open until 2009 or 2010. And then finally, necessary and sufficient conditions were provided. And so my goal with the remaining time is to tell you what those conditions are, and then show how there are some cases that are really easy to use those conditions, and then some cases it's just impossibly hard and you can't really say anything. So here's what I want to say. So I want to just introduce some notation in order to be able to state the result clearly. So for a left orderable group, set LOG to be the set of all positive cones. He is the positive cone of a left order. Now, we'll see in later courses that this, in some of the later mini courses, this is a topological space and you can talk about all sorts of interesting topological properties of it, but I'm not doing that. It's a set as far as I'm concerned. Now, it has an action of G on it. So there's a G action on LOG. conjugation. Right, and that's just because you want to take a group element G and act on P. You can just do this, and this is still a positive cone. So what I want to do is I want to call a collection of orders n inside of here normal if it's G invariant. Okay. So, and
Is that a right action by G?
sorry, what's that?
Is that a right action by the group
Oh,
G?
maybe
Because
maybe I should write it like this or something if I wanted to. Yeah, I see what you're saying. If you got to make sure that you don't define a right action by accident. Yeah. Yeah, it looked a little funny the other way, maybe. Okay. So this N in LOG is normal if it is G invariant. Now I'm ready to say what you need in order to order an amalgam. You have blue dog and glass. And I'll write it all down and then we'll talk about it for a second to make sure it makes sense. So I'll say suppose A, G, H as above. Right, so they're all groups equipped with these injective homomorphisms. Then this is left orderable, if and only if. Well, G and H are left orderable, of course. But also, there exist normal families. N1 and LOG, N2 and LOH. Satisfying, okay, let's write it. If you take positive cone in one family, there exists a corresponding positive cone in the other family, such that I'm going to write it as sort of pre-images of sets, but the way you should be thinking of it, all I, J, 2. So I wrote these as pre-images of sets, but the way you should be thinking about it is, what I'm saying is, every time you take an order on one of the factors coming from your normal family, there has to be an order on the other factor coming from the normal family, such that when you restrict to the common subgroup, they match. And it has to go the other way too. So it's like if I start with an order on G, coming from the normal family, and then I take an order on H and restrict to A and they match, I have to also be able to start with one on H and then find a corresponding one on G and restrict to A such that they match. And they have to be normal so that you conjugate, they're still inside the family. And so you see, I've said, for all I, J and 1, 2, well, if you choose I and J the same, this is saying nothing. But if you choose IJ to be 1, 2 or IJ to be 2, 1, it equals the symmetry of the situation. Okay.
So understanding if a three manifold group is left orderable.
Sorry, what's that?
In the case of three manifolds, like G and H are gonna be free from the Hölder splitting.
Oh, you're thinking of a Hölder splitting if G and H are free.
So yeah, so the question, like
so then
hinting that we can understand left orderings of the free group.
Oh, it's quite bad though, because you would need, yeah. So you need normal families of left orderings of free groups, and you have to track them under some identification. And I'll just say, yes, that is one way to attack the problem, but I think that's an attractively difficult question.
Yeah, of course. Yeah, of course.
But a Hölder splitting is not an amalgam.
Oh, it doesn't, you're right. Yeah.
Why? You don't have a surface subgroup of those, do you?
Yeah, it's not necessarily ending up being injective in the end.
Oh, when you say I see, so you mean that but IIs must be injective?
Yeah.
Okay.
Yeah, you're thinking the right way though, because what I want to get to, if I have time, which I probably won't, is that this is if you think about JSJ decompositions, for instance, let's just restrict to two pieces and you have an incompressible torus and you're gluing. It does say something in that case.
Okay.
Yeah.
And yeah, but the question I wanted to ask, can we describe the set of left orderings of a free group.
Not very well.
Fine.
Yeah, not very well at all. Yeah.
Cool.
Yeah.
Does this require a bijection between NI and NJ?
No, no, it's there's the way to think of it is there's a bijection between the restricted orderings. Yeah, but NI and NJ themselves can be completely different.
So for the future, amalgam means that the maps are injective.
Yes.
Or
For
for the past, yeah.
It changes everything.
Indeed.
Yeah, it changes
For my
everything.
future, for my future.
Yeah.
In school, they didn't tell me that. I should go to University of Pisa and aspect them. Okay, fine.
Okay, but okay, so the thing we're getting at in the questions that are being asked is that, okay, this looks good, but yeah, it's going to be nearly intractable in a lot of concrete situations where you have questions that you want answers. But there are some cases where it's really easy. Like, so for instance, let me just point out a corollary that happens for free. Is well, for free if you believe that this is true, right? I'm not even going to say any words about the proof of this because it's pretty difficult. In fact, I have a quick story. I committed myself to working through this proof, and I decided, well, it's going to work. I'll be able to do it if I just, choose G and H to be the integers, and A is the trivial subgroup, and then, I'll be able to get through the proof that way. But then, a few lines into the proof, they choose non-principal ultrafilters on each of the factors and start doing things like this. So you just sort of throw your hands up, and you can't really hold on to anything in the end. But it works. Okay, so corollary. So suppose A, G, H as above, and that G, H are LO, and A is infinite cyclic. Then the amalgam is left orderable. Why? We have to show two normal families that satisfy this condition. And so I just want to say, take all the orderings as one normal family and all the orderings as the other normal family. So take N1 equal to LOG, N2 equal to LOH. Done. When I say done, I mean, I realize you probably have to squint at it for a minute to convince yourself that it works. But the point is, if you take an ordering from here, this normal family, and you restrict it to the subgroup, there's only two possibilities for what it is, because A is infinite cyclic. It's the usual ordering of the integers or the reverse. And then I have to find a corresponding ordering from here that restricts to be the same thing. Take anything and restrict it. If it gives me the order I wanted, then good. If it doesn't, then flip it. There are sort of generalizations of this example where everything just miraculously works out. You can do kind of cool things where if each of the factors are nilpotent, then there's some result about every ordering extending and fun stuff like that. But what I want to focus on is, are there any, so here's what I want to end with is, are there any cases where the result of this theorem, I'll say more or less happens for free? And here's what I want to say. What's that?
Doubles.
What do you mean?
You take a double,
Oh, if you just take a group and then a subgroup and you identify it with itself.
double on the subgroup.
Yeah, I see what you're saying.
Doesn't work.
Yeah, I think that works out, but I don't know. I haven't written it down and I can't think on the spot, so I'll just say.
Apologize.
I know exactly which paper I would need to look in, but I can't think through it on the fly. Yeah.
Take the whole.
Yeah, you should be able to take the whole thing again, right? Yeah, you just take the whole space. Yeah. Okay. So, okay, here's my question. Is I want to investigate cases where this theorem works for free. And here's what I mean by for free. If that amalgam is going to be left orderable, then for sure you have to have something, a left order on G and a left order on H, such that when you restrict to A, they match. You have to at least have that. And then all this normal family stuff is kind of seeming like the extra stuff that will be hard to find, right? So my question is, are there cases where finding PG in G, PH in H with the restriction of the two So other cases where finding this and this with this is enough.
They're both by orders.
Yeah, that's the first thing I was gonna say. If they're both by orders, then yeah. Because what do you take as your normal family? You take this one positive cone and you take this one positive cone. And those are normal families because by orders are invariant under conjugation, the positive cones. So the normal family is one element. So observation from the audience, you've been reading ahead, is by orders work this way. By orders will work. And now I'll just end by writing out a very long conjecture of another situation that I think it should work.
So, Adam.
Yeah.
When you have bioders like this, doesn't necessarily, it doesn't imply, surely not, that the amalgam is biodegradable. It just means there is.
No, not at all. That's actually, yeah, open problem. When are amalgams of biorder groups biodegradable? Okay. So the conjecture is that this should be enough when the groups are three manifold groups. And it's JSJ decomposition. So they write this down. So I'll write it as a conjecture because I'm brave enough to do that. So suppose you've got 2 3 manifolds MI, compact, divisible, irreducible, and boundary of torus. Just for emphasis, incompressible torus. In other words, the inclusion of the Z plus Z is injective. So then fix some homeomorphism and be the two of these glued together by a phi. Then the fundamental group of M has this structure, right? Where it's I want to point. It's an amalgam, right? Where the amalgam is on amalgamation as long as it plus Z subgroup. And I1M. I'll write it this way. Where G is the fundamental group of the first piece, H is the fundamental group of the second, and A is the fundamental group of the torus with the injective maps phi determined by this gluing phi. So I'll just say for appropriate A, G, H, phi. Finding matching orders should be enough in this case, according to the L space conjecture. So, and finding PG and PH that match. By that I mean this should be enough.
Because in these cases,
Enough means.
By that I mean, i.e.,
what do you mean by
it makes the amalgam left orderable.
Oh, yeah.
Just by matching. And there's none of this normal family stuff to worry about.
So if I do a splice,
What do you mean?
like if I glue to like not complement, say, yeah, I mean 2 3 manifolds.
Yeah.
This must. So don't we know that this is not an L space only in case of an integral sphere gluing?
What do you mean? Like,
So if you glue and you get a rational sphere,
yeah.
we know that that's not an L space. Only if the gluing is an integral sphere. So in the rational sphere, you may get an L space sometimes.
Oh, I see. I don't know. I'm not sure. I don't know about this. Hey, Steve, can you, is that, I don't know this fact.
Well, where are you going with that? I mean, there's.
Yeah.
Sometimes
No,
you
no,
glue,
no,
you
but
get
I don't-
space, sometimes you glue, you don't.
Yeah, but I don't understand the meaning of enough.
Oh, all I mean is that if you find two orders that match under the identification, then that's enough to say that the amalgam is left orderable. Whereas in general, what you would need is you would need normal families, including the.
Oh, I understand.
No, you just
I
need.
match.
Yeah.
For a cusp hyperbolic 3 manifold, if you take sufficiently large Dane fillings, do you get orderability?
Well, not necessarily.
Yeah, I mean,
It could be like what's called a null space knot, where if you go in one direction, large enough, you're not gonna be left.
Can you find some sequence that does the job?
Yes.
So maybe to get your conjecture, what you could do is you could choose good sequences that are compatible, the two, and get some sort of quotients to the
Oh, I see, like you do some
to your amalgam along a cyclic group, and then you can knock out you can knock out your obstructions and get orderability like that.
So we have investigated like amalgams along cyclic groups to see how far you can get, and you can't get the whole picture. But yeah, it ends up being, yeah, that can take you quite far, but it didn't do the whole thing.
Does convexity help at all in this situation if the amalgamating subgroup A is convex?
Yeah. So if A is relatively convex in G or H, then it's another one of those or G and H, I should say. It's another one of those situations where everything's fine. And the reason it's fine is because you can take any ordering on the convex subgroup and it extends. Because it's convex, you can use some short exact sequence argument. And so then because any ordering extends, you can sort of build these normal families by just saying, well, if the ordering I need isn't in the family, just extend and take all conjugates, and then extend and take all conjugates. And there's some sort of iterative process to build the normal families you need.
A related question is, does convexity in the order sense have anything to do with convexity in more geometric senses?
Not that I know of. Not that I know of.
Can you restate that? Why is it that and if you have a convex subgroup, then any ordering on the convex subgroup extends to a new ordering on the whole thing? Is that obvious?
Yeah, it's like if you look at the it's not a short exact sequence argument exactly because the convex subgroup might not be normal. But being convex means that the sort of obvious ordering on the set of cosets works, where you just order using the coset representatives, and then you can pull back the order of the coset representatives and sort of push forward the ordering on the convex subgroup to make something lexicographic. And so, in fact, that construction I just described is independent of the order you push forward on the convex subgroup. So push forward anything.
So why can't you use that to get your conjecture then?
These A's are not always convex. There are situations like the peripheral subgroups aren't always convex in an order. In fact,
even for a torus.
Yeah, no. Like when it's a torus subgroup, no. There are situations where they are. There's situations where they aren't. Yeah.
You need the convexity for only one order, or like you need it for like to be convex for all orders?
No, you just need relatively convex, which means there's one order for which it's convex. Yeah, but then if it's convex for one order, you can make it convex for many by changing the order on the subgroup and things. Yeah.
We know at all like what normal families look like for Z squared.
No. The conjugation action on this, I erased it. The set LOG, the conjugation action on there is crazy. Like once you make it into a topological space, you can start asking about its behavior, and yeah, you get really crazy things like dense orbits and stuff like this. And it doesn't really.
Z square is biordable, so any normal family is just itself.
Yeah, we'll have coffee breaks in the other room again, and then we'll be in about 25 minutes.